What type of functional group is this?
Amide.
Right. And what type of functional group is this?
Amine.
Amines are nucleophiles and bases. That shouldn't surprise us because both nucleophiles and bases are electron donors, and the nitrogen has a lone pair that it's willing to donate. So amines are nucleophilic and basic. Amides are not nucleophilic. And non-basic. This might seem like a minor point, but it turns out to be very important. Amides are not nucleophilic and not basic. Why not? After all, they also have a lone pair. Why isn't that lone pair nucleophilic and basic? Well, can you draw the other resonance form of this amide? Here's the electron pushing arrows we would use to draw the other resonance form, right? So the other resonance form looks like this. Now, what makes a good nucleophile? Is something a good nucleophile if it's got a negative charge or a positive charge?
A negative charge.
A negative charge. So does this resonance structure make the nitrogen look like a good nucleophile? This is the explanation. If you just stare, you could stare at this picture forever and never figure out why this is not nucleophilic. It's only when you draw this resonance structure that you realize, oh, there's a resonance structure where this nitrogen has a positive charge. Well, nothing that has a positive charge is ever going to be a good nucleophile. Nucleophiles are things that have more negative charge. The only way to explain why this amide is not nucleophilic is by drawing this resonance structure of the amide, and then we can see there's a resonance structure where the nitrogen has a positive charge. Well, that's not the type of thing that would be a nucleophile. And by the same token, it's not the type of thing that would be a base, because bases also tend to be negative. After all, the classic base is hydroxide, which is negative. Something with a positive charge is not going to be basic or nucleophilic. On the other hand, amines don't have any resonance structures. So there is no positive charge on this nitrogen, so it is nucleophilic and it is basic. What's the consequence of this being basic? Well, since this is basic, that means it's willing to gain a proton. But that means that amines come in two different forms, protonated and not protonated. This is the not protonated form of the amine. And here's the protonated form of the amine. This is the same thing that we talked about for carboxylic acids a while ago. We said that since carboxylic acids are acidic, they have two different forms, with the proton and without the proton. So if your final product is a carboxylic acid, the last step has to be to figure out which is the correct form to draw. In acidic conditions, you would draw the carboxylic acid like this, but in basic conditions, you would draw it like this. Very few students can remember when they need to draw the carboxylic acid like this. This is something that's important to watch out for. Well, the same token goes for amines. Amines have two forms, so if your final product is an amine, you have to decide which is the appropriate way to draw it. So which of these would be the right way to draw the amine under acidic conditions? Because under acidic conditions, everyone should have as many protons as possible. Whereas under neutral or basic conditions, you would draw the amine like this. And again, it's very hard for people to remember to think about this. People almost always just take the non-protonated form, but in many cases, the protonated form is correct. So we'll have to watch out for that. None of these issues would apply to an amide. An amide only has one form because it's not basic. So we don't need to worry about whether it's protonated or not. The nitrogen in the amide doesn't protonate because of that resonance form. One thing you might have noticed is one thing that I keep doing today is on each problem, the first thing I do is I ask, what functional group is this? And the reason is because that's the habit you have to get into on your own. When you're starting the problem, you have to start by asking what functional groups are this so that you can ask yourself how they react. For example, you can't just say, oh, I know how this reacts because it's a nitrogen, because nitrogens can react in different ways. An amine nitrogen reacts very differently from an amide nitrogen, so you have to ask which type of nitrogen is it, amide or amine. Let's show the mechanism of the products here. This is a very important reaction.
Okay, so I was going to do a proton transfer here. How do I show
That would have been best.
Yeah, I just want to show
A proton transfer from here to here? Good, because we want this to be a better leaving group, if possible. And this is the way to show that. The nitrogen is going to donate its lone pair to pick up the hydrogen, and that will free up these electrons. Now this nitrogen started with a hydrogen, so in this picture we should include the hydrogen. Same hydrogen was here, and there should be a hydrogen here. I make that mistake all the time myself, dropping hydrogens on the nitrogens. We have to be careful about that. So now after the proton transfer, it has two hydrogens and a positive charge. That's right. That was the whole point of the proton transfer, to give it a positive charge. So that it would be a better leaving group. Go ahead and draw the whole structure here. That's fine. That's fine. So let's indicate what were our final products. Go ahead and point to the final products.
It's right here.
Good.
Acid.
And there was another product that we generated earlier. You don't need to recopy it, but what was our other final product?
It's right here.
Good. Okay. We're not really too interested in this. This is just the catalyst. But here's a product, and we were saying this was a product. Where did we have a mishap here with the proton transfer. So here's the mechanism for the proton transfer. This is how we can get the proton onto the leaving group to make that into a better leaving group. So minor technicalities, but TAs are picky about this. This should have a positive charge on the oxygen, because it's hydronium. That's the reason why. And also, you've got to show what's happening to these electrons. The best way to draw this is like I have it on the board, like this. So it's best to show the hydrogen attached to the oxygen, so you can show the protons moving onto the oxygen.